using. Nice. So welcome everyone for joining to this presentation. I'll be talking about solving the traveling salesman problem on DWave Annealers. And this presentation is prepared by me, but also I was using a conversation with Bing to answer some questions. So if there's any incorrect statements there, it's most likely from that thing, not from me. So and the other thing is I need to give credit to people who kind of made it possible, which is of course Katie, Sid, and Travis, organizers of this meetup, but also the content in this presentation was made possible by another Sid, who wrote this article on solving the TSP problem. He kind of basically is the brain behind how you do it. And then there's also, I apologize, I probably am not going to pronounce it correctly, but Zawosi, if I'm using it right, is another person who put together a pull request into Amazon Bracket Examples repository. And this used to work for about a couple of years up until DWave took their machines from Bracket, or is the other way, AWS removed the DWave machines from AWS Bracket. And so you can no longer run your programs in Bracket using DWave hardware unless you buy an AWS Marketplace subscription, which is 60 or 70 grand per year. So that's not something that most people can afford. And so, but I took the example that they've given and some of the sample data and was able to transfer it to what's called DWave Leap, which is basically just another platform that enables you to access the hardware. And I'll be showing a Jupyter notebook with the code. But I wanted to go through the slides first, just to give you an idea of how things work and what we're actually doing. So what is the traveling salesman problem? TSP for short. It's basically a computer science optimization problem where you're trying to find the shortest possible path to visit all of the cities, let's say on your map, or obviously you can have like a vision of a map that doesn't include all the cities in the world, right? It could be in a state, in a specific region, in your sales route. It really is the sales route is where it came from. And the path returns back to the city of origin. And the input is basically is a list of cities and then distances between the cities. So I wanted to say that this problem is difficult, and it's difficult using exact algorithms, which basically evaluate all of the possible combinations of routes, and basically it becomes impractical at 20 cities, and it's basically runtime complexity is bigger than factorial, which is really bad. Like for somebody who's not a computer scientist, think like just try to compute, factorial of 20, and that's the number of combinations that you need to process. And so on the right, you can see an animation that shows you kind of how the algorithm performs. It literally just goes through every possible combination. But there are other solutions that you can use. One is branch and bound algorithm, and the other one is held carp algorithm. And basically their complexity is a little bit better, but it's not much better. But they are also kind of like, I guess, semi-exact as far as I understand methods of solving it. And there's also approximate methods. So simulated annealing is an approximate method for solving TSP. And the complexity is actually not that bad. So I wanted to say what simulated annealing was, because it's in the examples and in the Jupyter notebook. It's a stochastic global optimization technique. Basically uses randomness to an optimal or suboptimal solution. And you can use either discrete or continuous variables with it. It works really well for large search spaces, unlike like SGD. SGD might not be as great. So it's a jack of all trades algorithm, and it basically, the concept of it is annealing in metallurgy. And I have some example that doesn't relate to metallurgy, but I think it might be useful to understand for a non-technical person. So the example I have is basically a 3D printing analogy, where annealing is also used in 3D printing, and I have a YouTube video even that kind of demonstrates it. I'm gonna just mute the video, but in essence, what they do is, you can see they've printed a number of parts that are the same, and then they, in essence, put it in an oven. And in the process of heating up the material molecular structure changes. Depending on how long the parts stay in the oven and what the temperature is, the strength of the material when you take it out from the oven will change. And it's similar in metallurgy, similar approach and similar results. And there's a whole like physics behind it, but I'm not a physicist. I am a software engineer, and so I can't talk much about it. And so what they do in this video, they've printed a lot of the parts, and they're trying to find what is the best temperature and time to keep those parts in an oven, so that they're the strongest. And you will see that later in the video, what they do is basically they have a machine, well, they measure everything, but they have a machine that tests the strength. And here, basically, it just like hammers the part, and they see like, I guess they measure the strength using this machine also. I don't know how exactly, but they give you basically an idea how the temperature changes and how the strength changes with it. So, and what this is also, the analogy for it is sort of hyperparameter optimization. They're really trying to find the best value of that hyperparameter, which is temperature. So I would say doing simulated annealing and quantum annealing kind of, to me, is at least the way that I understand it, is very similar to this. And in fact, I had a slide, I don't know where it went, but I had a slide that also shows you kind of like the view of simulated annealing, where the line jumps randomly. And basically what simulated annealing does, it tries random points in your search space and evaluates how well they work up until it hits that one place. And it's not just like, there's some more logic. I'm like dumbing it down basically, but that's in essence what it looks like. So the other thing that I wanted to mention is, what is a DWave Annealer, right? Like DWave is basically a company that produces this fancy hardware that costs a lot of money. And the video here shows kind of a tour of their lab. But in essence, this is what it looks like. This is the chip that they show here. I don't know why. Okay. Yeah. So this chip, and you know what? I actually think I have an older version of the slides for some reason. I'm not sure what's happening, but this doesn't actually have some of the details that I was gonna put together. This is, hold on. Okay, I need to refresh my slides because this is literally not all up to date. So give me a second, I apologize. I got signed out, and hopefully this will actually refresh the slide for me. Apologies for that. And actually interesting, because I was working on this computer. Okay, so yeah, so that's why I wasn't seeing the diagram. so in essence, this shows you like basically just randomly jumps and jumps until it finds that place. But there's some logic to it because, well, what is the difference between randomly jumping and just exhaustively looking through all of the options, right? So there's some more to it, but we don't really need to like know about that. Okay, so DWave Annealers. So and this is another video that also is a tour. This is what the actual machine looks like. So there's 3 racks next to basically a room, and inside that room there's the actual device. It's
and I'll take us through
cryogenically cooled, and he shows here the parts and what it consists of. But in essence, you saw that chip that I showed you in the previous video. And here on this video, he's showing kind of a logical view of that. It's basically a grid, and you saw it like there were more cells in the grid, but each cell basically is a superconducting wire loop. And here, like on this diagram on the bottom, it just shows it kind of logically what it. Of course, the loop physically looks, I guess, more like a square from what I see. But each loop basically is superconducting wire, and I guess that's why you need to have super cooled, basically like really cool temperature in this room for this to work. But in essence, the superconducting wire loop simulates a qubit with its magnetic field, and so then you have magnets that control the state of the qubit. And then in order for you to achieve entanglement, you basically use what they call couplers. I don't know like the physics behind how they couple things or how they work, but that's kind of basic understanding of what DWave Annealers do. And you can watch the videos in the slides and get a better idea. Okay, so and so they call adiabatic quantum computers. So what does adiabatic mean, or adiabatic? I don't know how you say it properly. Probably Australians say it differently. But it basically it represents a process where heat doesn't enter or leave a system. But in our case, I guess it's not. Well, it's super cooled, so maybe it's heat, but to me, it's probably magnetic field. They are basically shielding that room from magnetic fields, and I think that's what really is meant here in case of quantum annealing or quantum adiabatic computers. And the idea also is that the other key characteristics is that the thermodynamic process is slow. So it's like the system, basically system has enough time to stay in equilibrium state. Like it doesn't like blow up or whatever, or does something extreme in the process. And we assume that the heat exchange is minimal, which is what, like again, with quantum, like magnetic fields basically are, effects of magnetic fields are negligible. And in quantum mechanics, the analog to equilibrium is basically an eigenstate, which is either an up or down, or zero and one, depending on how you want to look at it. All right, so a more scientific description, if you're like really into math, you have a system of qubits that are in initial state, and that state is described by Hamiltonian, and then you slowly evolve that system, and I'll show how, try to explain at least how they evolve the system in the quantum machines there. But in essence, you apply magnetic field to evolve the system, and the system eventually reaches this state, the final state, which is described by Hamiltonian H1, and that Hamiltonian really contains your answer that you're looking for. And there's a theorem of adiabatic computing, quantum computing, but it basically, it's the basis for this thing that makes it possible for this thing to work. And so yeah, so we're basically trying to evolve the system slowly, and the idea is at the end, qubits assume minimal energy state, and that's if you're doing an optimization problem, you're typically either looking for a maxima or minima, right? And so this is exactly what you want. So the a more detailed description of what they actually do is, I just describe it with 3 words: entangle, evolve, read. So you kind of achieve the superposition state, and the system is in kind of high energy state. Then you start applying magnetic field, and you kind of get this kind of so basically a superposition right here, right? Because it's not in an eigenstate. So then you let it evolve, and at the end, you read out the best answer. That's kind of how I understand it. Not very scientific, but again, I'm not a physicist. All right, so the differences between simulated and quantum annealing. So with simulated annealing, you basically like your energy, I guess, is temperature, and then in quantum annealing is the strength of magnetic field that really is sort of acting as energy. That's kind of how I understand it. But also the difference is the your qubits, they all change at the same time. I guess with thermodynamics, I mean, your molecules are also all changing at the same time. So not sure if that's really distinctive characteristic. All right, so how does DWave solve it? Because what I showed is like great, but like how do you take the traveling salesman problem and use those techniques that I described and somehow arrive to a Hamiltonian that gives you the optimal or suboptimal solution? So the way that they achieve this is they map TSP problem to QUBO, which QUBO stands for, it's the next slide, I'll explain, but quadratic unconstrained binary optimization. And then in essence, DWave encodes the QUBO problem onto the actual hardware, you know, those superconducting wires and couplers. And then the process is repeated a number of times. And because solutions are probabilistic, it's the same with the IBM machines, where you have to rerun the same experiment a number of times and then measure kind of the average of what you're getting. And so repeating the process basically increases the chance of finding a better solution. And you can control how many times you rerun sort of this experiment. But they charge you. They charge you for time. And so, but even though they say that it's interesting, because when I was reading their description, they say that if you're going to a higher number, it's actually not taking a lot more time on the machine. So, but I've not really tried changing the number of experiments. So what is QUBO? Like I said, quadratic unconstrained binary optimization is basically a mathematical problem that you can formulate in a form of an equation. And the equation will have like binary, linear, pairwise quadratic variables, and it may include constraints. It's interesting because it says quadratic unconstrained, but it may include constraints. And what unconstrained really means is that the solution to this equation can violate the constraints, but you get penalized for violating constraints. And so what, in other words, what it allows a quantum computer to do is to find solutions that satisfy constraints without forcing the constraints to be satisfied. This is contrary to, like, if you were doing a classical algorithm, you'd literally have some sort of a routine that checks, does this solution satisfy this constraint and this constraint and this constraint, and you'd run over all of the solutions many times to find sort of one that satisfies that. All right, so how do we build QUBO for TSP? And this equation I basically just stole from Sid's article that talks about how to solve this problem. But in essence, you build an objective function. Sometimes I think in some contexts called like cost function or loss function, but here they just call it objective function. And the idea is that this equation looks fancy, but in essence, you see the sum here, and this is the sum of going from one city to another. So Mij is basically the distance between the distance that you need to travel to get from CTI to CTJ, and then Mji is the distance you need to travel to get from CTJ back to CTI. And it's not necessarily the same if there's no direct path. And then Xij is basically it's a binary variable, right? That tells you it's 1 if the nodes are adjacent and 0 otherwise. And you can rewrite it as just this sum of b variables. And what this is missing though is the constraints, and the constraints that we have. So in traveling salesman problem, you can solve the vanilla problem, but if you want to apply it to logistics, the vanilla problem just deals in distance, like what is the distance between 2 cities. But in logistics, it's not just distance, right? You also need to weigh in, like, what's the cost of like gasoline, or whatever, jet fuel, or whatever you have, or what's the capacity of the airplane that I'm using or the train that I'm using to transport goods. And so if you look at this equation, there's no way to write that in. All it has is the distance, these two factors, and you can't tell it like, I'm specifically looking for solutions that are favoring maybe not the distance, but they're favoring like fuel consumption. So there's really no way to encode that. And this is where they apply what's called the Lagrange multipliers method. And you see that the equation ends up with this additional term that has lambda in it. And lambda is called Lagrange multipliers. And the way that I understand it is this additional term is basically a way to penalize or reward the objective function for finding solutions that kind of, basically it's a way to tell, is this solution closer to satisfying my constraints or not. All right, so next thing is sampling. What happens is basically the process of repeatedly running the problem on an annealer. So you sample different solutions from the machine, and the solutions are not guaranteed to be optimal. They can be like suboptimal, or actually can be non-solutions at all. That happens too. When I was preparing for this presentation, like I was able to see some examples where I just get garbage solutions that make no sense. You can then pick out of those kinds of solutions and pick sort of the best one that you got. And the DWave solver for TSP, it already picks the lowest energy sample, but it only picks from the samples that it has, depending on, let's say you do 1,000 tries, or I think they call them reads. You only have 1,000 samples, so you might not find the best one either. There's also a term that they use, BQM, which is basically a more generic version of Cubo, and trying to talk intelligently about it, but in essence, all we need to know is really that DWave has this Ocean API that allows us to interface with the machine, and it accepts binary or spin problems. And spin problems are icing problems. I don't even know exactly how that works, but supposedly icing problems are slightly different. Exactly how, I have no clue. So that's basically it for the slides. And then I'm going to jump into the DWave Leap platform. So let's see. And I posted link in Meetup group, but what you could do is you can register here. It's absolutely free. So when you go, and there's a nice picture of the actual machine. I'm going to need to authenticate here. Hope I can get the access code.
Does anybody have any questions or comments so far?
Oh, this is sending to my this is sending the code to my email. Sorry, I was looking in my authenticator. Okay. All right. So when you log in, what you'll see is this landing page that shows you demos. You can explore examples, and you start out with a trial plan, which gives you 1 minute of the time each month, I think, on the machine. Or no, for the first month, you get 1 minute of machine time. And you can get more time. You can upgrade to a developer plan. If you post your code publicly on GitHub, they will upgrade you to developer plan. This is what I did. But all that this is doing is you still get 1 minute, but you get it every month. I think that's the only difference really between the plans. And if you look at this, you will see that there's different solvers. So there's QPUs, quantum processing units, and there's only one really in Europe, but there's a few devices in North America. There's this hybrid devices that I don't actually know how they function or what they do or if they're better somehow, but they're also able to solve BQM problems. I don't know what CQM or DQM are, but the example that I'm going to show is running on an Advantage system, which is just purely a QPU. Let's see. So when you come here, there's on the top there's an ID workspaces area, and if you go there, you'll be able to create new workspaces. So you can just create one and paste your GitHub repository, or you can pick from the examples that they give you, and they have quite a few examples. But here I already created a workspace, so I'm just going to start it. And I posted the link to this in the Meetup comments. So I'll start with just kind of basic stuff. So what we do initially is just import a bunch of routines, and you will see that there's a few things we use. DWave Network X. So Network X is like a Python library that allows you to basically interact with graphs. I believe that's what it is. I'm actually going to Google it just to make sure I don't misinform it. Yes, that's right. That's basically network graph library. And I guess DWave has their own version of it. I don't know why they would need to do it, but my guess is for the hybrid systems, maybe. There's also DI mod. I'm not quite sure what this package is, but as far as I understand, that's also DWave. Let's see. And so also matplotlib is used here to just show the problem visually. And this DWave system, this is coming from what they call DWave Ocean. It's basically like a suite of different tools that they give you to build applications and run experiments using their hardware. So I'm going to run the import. And it takes a while for it to run, but that's finished. And I have some sample data set that I'll show in a moment. So the way that the data is encoded in the sample data set is very simple. It's the nodes or cities, I call them nodes because they're in a graph, but the cities themselves are labeled 0 through 1. And then you can find out the distance between each city by looking at, let's say, city 1. How far is city 1 to city 3? And you see it's 6. So we're assuming that they're all kind of connected. And if they're not connected, a way to still produce this table is just find paths and then calculate the distance from the two disconnected cities. So then we can, like in this example, see the distance between two cities, in this case city 0 and city 1, and it says 3 right here. We can also like count the number of cities in this example. That's very simple. There's only 5 of them. We fix the seed so that we have reproducible results for simulated annealing, because simulated annealing, like I said, uses randomness. And so if you want to see repeatable results, you want to basically have the same seed. This example just kind of computes, well, as far as I understand, I need this to plot the actual graph, and you will see that in a moment. The weights, basically those are the distances right here. And so you can see the graph now, right here when I plot it. So you can see that you can get from every city to every other city here. So fully connected, and you can see the distances. Now, this is the part where it's doing simulated annealing. So I'm calling this method called traveling salesperson, and I'm giving it a sampler, but the sampler is actually a simulated annealing sampler. So when a solution is evaluated, the solution is not being produced by a quantum machine, but is being produced by a classical sort of machine using the simulated annealing algorithm. And I also timed it just to see how long it takes to run. Right. So in this case, it took 4 seconds. It's not really like representative, because if you rerun it a few times, best thing is just to average it out. But I didn't do it for reasons that I can't really. I don't think I have enough machine time on the quantum machine, so I can't really like run 100 of examples and then average out. So I just did 1, but it's kind of close, like 4 seconds. That's the time it takes. Now you can also do an exact solver, where the exact solver basically is doing an exhaustive search of all the possible solutions. And here you can see when I ran it, it took 1 minute and 30 seconds. So if I start like adding more nodes, it will quickly take hours and days and months and years. And so that's why we try to use other algorithms, and that's where quantum annealer comes in, right? Where, yeah, simulated annealing is great. You can still kind of solve it on a classical machine, but maybe you can do better with a quantum annealing. And so I have to actually wait for this to finish. I'm in the 30, and so now would be a good time for like questions if anyone is curious, wants to know anything. All right, I guess there's no questions. I'm gonna just then continue talking about some of this. So this example just talks about kind of getting the distance between two cities, and it's specifically in the final solution. So the distance here is basically that shortest path, shortest loop, if you will, through all the cities. That's what this really is talking about. And this number is needed to compare the solutions. So then you run simulated annealing and you get the distance, and you can compare it with the distance you got from the exact solver. And then you can compare it with the distance you got from a quantum solver. So then you can say, like, which one is actually giving me the optimal solution, which one is giving me suboptimal solution. This is like a snapshot, really. It's not meant to give you exact, it's not going to be consistent results either. But you can see here, it took a minute, 30 seconds roughly to run. So then what the distance was with the actual exact algorithm is, let's see. So with the simulated annealing, the distance was 17. I have to replace this variable. I'm just gonna duplicate this and use the other variable. So here I store the exact route in this exact route variable, and I'm just gonna plug that in. Okay, I think I may have broken something, you know. Okay, I feel like I may have broken the code here, but one sec. I'll try to fix it. Okay, I did break it, and I think this is where I broke it. So the exact algorithm found obviously the best result, but it took a while. But the distance was 15, basically the most optimal loop. And you can also print out the loop by just basically printing out this variable. I actually printed it out right here, but so this you can kind of see what the route is. I'm not sure though why this is strange, because when I look at this, they're actually the same. So I'm not sure why the distance is different. This is strange. Yeah, I'm not 100% sure why. But let's move on. It's okay. I think that there's probably some bug in the code somewhere.
So you have total distance, return distance, and distance. Right? Total distance. So you're printing total and printing total. I don't know.
Yeah, this is interesting. Well, and one way to just troubleshoot it, just to be sure, is do this. Do exact route and route. Yeah, so the actual route, the simulated annealing, and I don't know why this output didn't get updated. Okay. Oh, I know why. I scrolled through it and I didn't actually run it. So that's the problem. I never ran it. So, okay. But yeah, that's where randomness comes in, because you're gonna get different results. So now this is right. And when I was originally putting together this presentation, it was slightly different.
Okay.
But yeah, so they are different, and this is the problem with simulated annealing, is you're going to get different results different times. And what people do when they use it in real life is they'll run like number of iterations, and then they'll pick out of all of the results the one that is the best. So this is also including the return path, but I'd have to compute this. And so the distance between start and end, and then total distance. This is just for the simulated annealing, and I can reproduce the same for exact solver. So let's see. And that should be, oh, that's interesting. Okay. not sure why this would be different with exact. But anyway, I think I didn't mean to actually show any of this stuff, like any of the distances, but it's useful to just even see the total distance difference between exact and simulated. But the next part is running on a real machine. So, and the way to do it is we have to use this embedding composite, and then we give it a DWave sampler. And embedding composite is the thing that converts, basically converts to BQM, as far as I understand. And then it sends that into the machine. So it's kind of like a sequence. Start out with BQM. Well, start out with a graph, then convert to BQM, then convert to the actual sort of sequence of signals for the machine. I don't know exactly how they represent that, the signals there. So when I run this, what you will see, and it takes a bit, it took 2 seconds. I can rerun it again. And part of this is also sending and maybe that's where the hybrid systems are useful. Part of this is sending the problem to the server racks that you saw in a video, the 3 server racks. And then the server racks do something, and then they convert this and create signals, and then interact with the chip that you saw that is inside the room that's cooled. But you can see it's roughly 2.60 seconds, and it's not going to change too much. But what happens when you do this, if you go back to Leap, you will see that, let me refresh this. You will see that the run will be recorded. So just a minute ago, I ran the problem. It's not labeled. You can like attach labels to these problems, but it also tells me that today I completed 2 problems because I did 2 runs, and in total I utilized 31 milliseconds of the machine's time today. I can run it through the whole like time, and I didn't use any hybrid machines so far. So this way I can kind of say that on the actual machine, roughly took about 16 seconds, right, to run the problem, or sorry, 16 milliseconds. So that's actually not bad. But why am I getting 2 seconds? That's where I'm sending the problem, I'm waiting for it to come back. But I think also this could be the queues. I know that, you know, the IBM people, your problem kind of gets in a queue and before it runs. So that maybe that's what it is, because these machines are shared. They're not like, you know, like I get exclusively my machine. That's where you pay 70,000, right? All right, so let's see. The next part is the inner working of this code, how it functions, and what they call hyperparameter optimization. So I talked about those Lagrange multipliers, and basically we can randomly pick one and just run with it. But what kind of result are we going to achieve? And in fact, when you look at this example, I'm not actually providing any Lagrange multipliers. So are they really an input? So if you look up traveling salesperson DWave, you will get their developer portal with the description of the API. And in here, you'll see that Lagrange is actually an optional parameter. So you can provide it, but you don't have to. And they're basically weights. And I think the reason why they like use the term weight, because like I said, it's not necessarily distance. But here they're saying like, the way that I understand it is the smaller it is, I think you're aiming for shorter distance. Larger it is, it's like the shortest distance is not as important. That's kind of how I understand it, but I'm not 100% sure.
Well, another thing, like for a constraint or a weighted constraint might be time. Like I have 15 stoplights this route, but this other route I only have 6. So you could weight it at the number of stoplights.
Yeah, I think that's exactly what it's for, is to give you more flexibility, because like the real world problems, they have this complex constraints. But
Right.
here I'm just showing a toy example, right? So, and the idea is that you might need to play with the Lagrange multipliers to tweak them to give you the most optimal solution. And that's in essence what they call hyperparameter optimization is. And here in this example, I basically produce a list of, oh, well, why is this complaining? Oh, that's right. So somewhere in here, I should have it defined, and I don't see it defined. Oh, that's right. I think I need to start out with, let's see. Trying to remember, maybe I need to rearrange this stuff. Yeah, so if I randomly pick like Lagrange, and this is called Lagrange parameter. So if I pick it for hyperparameter optimization, basically I'm looking on the left and on the right kind of this, and they have some complicated formula to figure out like exactly how you build like this list. But honestly, I think it will vary problem to problem. So this logic of like, how do I pick the list of different Lagrange parameters to try? I think it will be like specific to your problem, and you have to experiment. And this is where like all like really domain knowledge comes in, and like this number's 0.8, 1.1. I mean, what do they mean? So that's where like you have to, I think, apply business knowledge to really come up with this. But in essence, you'll have some idea of like what is the range of Lagrange parameters that is sensible, and then what you do is you, in essence, run this code, which to be honest, I don't quite understand, but it has some logic also built into, and they explain what it does, but it has some logic basically of picking one that seems to work best. And here, I don't actually see that it changed anything. So I think, yes, I think what this does is if I had, yeah, if let's say I start with just, it's basically a way for me to know this number, right? So here I just randomly picked 24. I could have like picked 30 and I would have gotten a different set of parameters. And this is where that sort of business logic, if you will, or domain knowledge comes in, and they describe what, how they picked it. And in this case, they're basically saying, I just need an average length of the tour. That's what they're looking for. And they're looking between 75 and 150%. So then if you run it, in reality, what you end up having based on this graph, and this will be different depending on the graphs. So the number will be different for another graph. So then you'll end up with 24 as the parameter. All right, so then you can, so when you look at DWave developer portal, you will see that they have two methods. They have, or two API, traveling salesperson and traveling salesperson Kubo. And if you call, because I think most people, you don't need to be a genius to interact with a quantum computer. I think that's the biggest message that I have for everyone. And you don't need to have a PhD and know physics. In reality, is the API that you're given is basically, as long as you know how to pack your problem in a graph and pick some sensible Lagrange multipliers, you can send it to the machine without having any knowledge of, qubits and any of that. And so, but under the hood, what this traveling salesman program actually does, it invokes traveling salesperson Kubo method. So, and I wanted to show you that. So the source code can be obtained on GitHub, and you can see the traveling salesperson function in its source code, and it's actually doing what I'm gonna go through in a moment. But the first thing it does, it calls this traveling salesperson Cuba. So basically, the first thing it does, it takes your graph and converts it to Cuba. And then it calls the sample Cuba, which is basically a way to say, go send this problem to the real quantum machine and get me the response. So here, that's exactly what I'm going to do, is first get the Cuba. And the way this reads, when you read that documentation, I think it's actually not up to date, this documentation that they have on their developer portal. Because when you look at it, you will see that the output should be these pairs of C and T, where C is a node and T is a time index. But to me, a node is basically like 0 or 1 or 2, right? That's how we labeled CTs. But when you look at this output, it's actually 0, 0 or 0, 1 or 0, 2, and there are pairs of them. So I think they changed the output, but they've not updated the documentation. But suffice it to say, this data structure contains information to build that equation that I was talking about, the Cuba equation. But I think this is optimized to be sent to the machine. And if now what this is going to do is going to run this Cuba on the actual machine. So when I run this, and of course, I'm missing something. Let's see. Oh, I know what I'm missing. So I need the sampler, which is this. So I'm going to create it real quick. Okay. So this is going to send it to the real machine, and you will see that now I have 3 problems today. Well, that is interesting because I I don't see anything that okay. What is what is happening here? This is interesting. It should have, but I don't see that happening. So
Is there an error?
Well, unless this is not updating. Oh, it's not. Okay, this is not updating. That's right. Okay, there it is. So perhaps it's not like real-time updates, but here you can see it's 23:24. It's I guess UTC or GMT time, but the response is kind of gibberish when you look at it. It's some array and talks about energy. Less than, I assume this is less than F8. I have no way of reading it. I think this is like literally internals of how they measure things and how they operate. And perhaps there's a way to read this. I think IBM machines also spit out a bunch of like diagnostic stuff you can read, but I'm not an expert. So to me, these numbers don't mean a lot, but timing is interesting because you can see like sampling time. And I assume this is not even milliseconds because it takes only 15 milliseconds to run the whole thing. So maybe it's like fractions of nanoseconds. We don't know the unit, unfortunately, here. But you can see, I think it's probably nanoseconds, but I might be wrong. Like I'm honestly not sure. And then per sample, right? So I think the default number of samples that it runs is 1,000, if I'm not mistaken. And readout time, you can look at this kind of if you know exactly what you're looking for, but honestly, like to me, that's gibberish. And all I understand is binary, which is, you know, I'm running a Cuba problem. Yeah. But now what I do is there's a field called first, and then there's a subfield called sample, and that's really what the sample is, the actual answer. That's what the machine found. Basically, it's converted from the eigenstate from the Hamiltonian back to the language that I can understand, which is the graph nodes and 0, 1 basically means I think that it means whether it's in the solution. And the way that they use to convert this into an actual route is iterate through this, and basically if, well, this is interesting. Yeah, if there's one, then it becomes part of the route. And so, and then I think it's the first item in the, or the first element in this tuple, in this little vector, denotes city. And then the second one is time, which is when do you visit the city. So in this, the way that I read this, you visit city 0 second, and then I don't know if there's one with 0. Yeah, so you visit the city 2 first. But the problem is that you typically know your point of origin, right? So the machine just told me, like, wait, you visit the city 2 first, but I'm in city 0. So this answer doesn't make sense. So then they have some interesting logic to, in essence, to and like if you actually, okay, so let me just make sure to rerun it. If you run this code, what you end up is this, which is not even an answer, right? This is nonsense, because, well, I have a none, 2, 3, and 1. And this is where, like, this is where you are not always getting even an answer that satisfies. This is where unconstrained, right? You can get basically stuff that doesn't satisfy the constraints. And so that's where you have to run it a number of times. And this is where they have some logic in their code to say, if you want to start in another city, this is a way to build an answer. Here, because this answer isn't even, basically it's not a valid answer, the code doesn't even run. And this is because I'm manually reproducing what, and if you look at their code, looks familiar, right? This is exactly what I just ran. And this is also exactly what I ran in here. And the way that I understand it is they, like, basically they can spit out this to you, and you have to rerun it again to find something that's reasonable. And so now I'm going to try to run a larger problem now, which has 10 cities. And so I'm going to load it from a file. This is the actual distances matrix, if you will. This is just something I used to build the graph. So this is what the actual graph looks like. And then this is going to try to run the exact solver. So I'm saying solve the traveling salesperson problem with the exact solver, and start your start point or start city is city 0. And what's going to happen is immediately it's just going to refuse doing it, because it will say that actually, what does it say? Maximum allowed dimensions exceeded. And what it means is they're not going to even attempt, because this will run forever and it's going to, like, just waste money. So they're not even going to run this problem for us. I can run this on a simulated annealing on classical hardware. And what I will get is, let's see. Oh, well, this pressing, okay, just misclicking. And this will take longer because the problem is bigger. So now you can see, like, in reality, like, if you're solving, so this is where I worked for a company that was in logistics, and we were working in a warehouse where we're trying to find optimal routes for pickers to go through the warehouse and pick items. And they're not cities, but they're shelves, and you have thousands of them. So this is where, like, you saw, it's still running, right? This is still running on simulator annealer. It took 30 seconds to run this problem, and it's only 10 cities. But if you look at a warehouse, you have thousands of shelves, and technically they are all, you may have, like, to pick an order or a set of orders, you may have to visit, you know, hundreds of shelves, and you have constraints, like things like you wheel around a cart where you put the items for your orders. So the cart has capacity, and the other thing, you have other constraints like you need to get the orders out in a certain time, and so you end up with all this constraints. And we were also trying to, on top of just grabbing the items, to reshuffle them. So you start having this complicated constraints, and you have thousands of shelves, and you're trying to basically evaluate so many different ways to solve this problem, where literally sometimes it took like hours, like 8 hours to solve the problem using classical computers. And so that's where basically the promise of quantum computer is that, because you're able to process all of these different combinations kind of in parallel, you're able to get to the answer quicker. So now I'm going to run this with an actual quantum machine. And here again, it's sitting in the queue, sending it to the machine. I think that's where the hybrid machine is probably, and we can actually give it a try. We can try the hybrid machine now and see, maybe it's going to run faster. I am actually curious now, but it's still running. One thing to note, it will be slower than simulated annealing, as you can see already. But again, I think this is where, at some point, when you have large enough problem, this becomes faster. That's kind of how I understand it. But I can be totally wrong. This is where I've not really experimented enough to tell you that, hey, at 1,000, CTs, quote unquote CTs, could be shelves or something else. It gets faster. So here it is, right? So this is the random nature where I got a non-answer again. This is not even a proper solution. So this is where you basically, and even if you solve it with a classical computer, you still have to run the same thing, because you're going to end up with non-solutions in the result, and you have to basically say, it's a non-solution, reject it, rerun it again. And that's where you get hours, because you're doing this. And we can see how long it took to run. Well, I have to subtract. I have to compare and subtract what it was before. So now it was at 63, roughly 64 milliseconds. And then when it finishes, we'll see what it will be. So I kind of get an idea of how long it took on the machine. But I could have also gone with the approach of just running the sampler directly and getting the machine readings that I was showing you, wherever they are, right here. And I could have found out, all of those metrics from the sample itself. Okay, so this time we got a solution, right? So this is a route you can see is different from the original route. And I think one thing to try is, let's compare them, right, in terms of at least total distance. So let me grab that example that I had. Yes. Okay, that is so confusing. So this is another thing. So even though this looks like a valid sequence of numbers, I think what may be happening is that this is still not a solution. Let's check. This is gonna produce the same result, but I want to replicate it and rerun it again. And basically, what I'm looking for is, and I think the reason why we're getting an error is the way that this is computing distance is, well, it's a connected graph, so I'm not sure why I would get this. Oh, I think I may know. Data, that's right. So, okay, I was using data refers to that small problem, the 5-city problem, but the variable that I used for the big problem is called data 10.
Oh, okay. That would explain why you're getting weird.
All right, so I'm gonna give this a shot again. So I reran the problem, and you can see on simulate annealing gave me a different route again. So now I'm gonna compute distance. So the distance is 336, and then let's try to do it for the quantum machine again, because I'm using the same variable name, so I overwrote whatever I had before. But let's see how long it took last time. So it took, well, I was at 64, so it took 15 milliseconds. So, and they say the number of readouts really doesn't change much. So I could bump that. Okay, let's see. And the way to bump the number of readouts is when we were looking at the sample QBO method, I think it's on the sample method or it's on the sampler itself. Yeah, so they have this parameter, and you pass it in. Yeah, so you actually pass it into composite, which is basically the thing that converts your graph into BQM. So it would be right here where I would do it. In the embedding composite, I would just add reads and basically get a larger number of reads. But by default, they say that it will be somewhere in here. From memory, I think they say it's 1,000 times is what they do by default. But I honestly don't trust documentation because I saw it being out of date somewhat. Okay, so I think this time I got a non-solution again. Oh. And how many seconds did it take though? Because I'm
15 milliseconds.
right, but in terms of complete time, right? Because we're waiting for the problem to get sent and sit in the queue. I'm curious what that is, and obviously that probably varies with the load. Because when they have more load, you'll wait longer.
Right.
But to me, it's still a factor that you gotta consider. Like, if your runtime is larger than the wait time, then significantly larger than the wait time in the queue, then it's not really a problem. But if your wait time exceeds the runtime, you might as well just use a classical computer at that point. And I think this is where you balance like the problem size, the wait time, and the runtime to get the best results. And while this is running, what I want to do is create one that is using a hybrid system, just to kind of finish off the presentation, because this is really the end of what I wanted to show. So I'm gonna, so instead of DWave sampler, now there are other samplers. DWave hybrid. So there's a lot of samplers. I think the reason why they have so many samplers is for different types of problems, because what I'm doing is just traveling salesman, but you may need to do some other things. That's my guess. But I'm trying to find documentation that actually tells me. And I've seen it. I've seen the in the documentation that lists them all out. I'm not sure why I'm not finding it right now. Perhaps I saw it in the examples, but anyway, let's go back. Hopefully it's giving. Okay, so did it finish or not? It's still okay. So we got a non-answer again. That's where like you'd be running this over and over. And maybe what I should do instead is set the non-reads to a larger number. Make it like. They say it's not going to change runtime much, right? So let's test that suggestion and just run 100,000 examples. And so if you had used AWS bracket, they charged per number of tries or reads. Which was still affordable, like because
did that run? Did that kick off?
Oh, I'm still waiting for the other one to finish because I can't like resubmit it again. So I have to wait. But while it's running, yeah, there it is, Leap Hybrid Sampler. So that's what I need to use to try running this on a hybrid machine. And so with the trial and developer plan, I think you get not 1 minute, but you get like an hour of the hybrid machine time. So you get a little more. I think it takes 1 minute and 30 seconds, if I recall, to get an answer from this. But I should take note. Maybe it takes more than 30 seconds. Okay, so this time we also got a non-answer, but at least it didn't crash because non-answer because there's none. So now what I have is 100,000 reads, but I assume that embedding composite actually supports this argument, but that's where their developer portal doesn't really doesn't tell you much. Yeah, see, this is not something that you can give it. So just check. You can't pass in the parameters. Oh, I see. So this is where like this knowledge of the source code. So it should be going into sample Cubo for the sampler, but my guess is this is just an unsupported feature, or maybe I'm not doing it right. I could try Googling composite reads. There are examples that are using that, so I'm not quite sure why I'm not, why it's not working for me. Oh, so this is cutoff composite. My guess is not all of this composite functions support the number of reads, and this is where it's kind of a learning curve, I think.
Well, which is the intent of this, right?
Yep.
Is to try it out together and figure out what it does and how to do it.
Yep. So let's try running it on a hybrid machine, and see, maybe it does better. And I do need to import it. Go back and import that. Oh, it's not composite.
You need to say import profit, or does it know?
Oh, I mistyped. I mistyped it. That should run now. Okay, well, that's the problem for another day. So I think that my guess is this also this composites. You can't just use any composite with any machine. That's my guess, but I'm not gonna claim it 100% that I know what I'm talking about, because I'm still learning this. But I hope this was useful just to demonstrate like how you can run on a quantum machine and some of the challenges that you're going to run into when you try. And some of the concerns that you would have when you try to solve real world problems on this thing. So thank you folks for coming, for listening. I'm glad I got this chance to present, because the biggest part of this for me was while preparing, learning this stuff, because I've done this with bracket in the past. And so for me, it was like fairly easy, but on directly on DWave, it's a bit different, like this whole setup. And I can probably show you what the bracket version of this looks like, just kind of a skim version of this. And it's on an older machine, and they go through like all the equations, all the math, but in the end what you end up with is they use bracket API to interact with the machine, and they specify the machine. And let's see if I can find. So this is literally kind of a clone of what I'm cloning what they're basically doing. And a lot of it is the same, but for bracket, when they get into bracket stuff, they just use this different sampler basically. Mm-hmm. But largely it's the same approach. So yeah, so that's it. That's all I had. Thank you.